Hi, my name is Scott. I'm from the Economics Tutoring Center at Arizona State University. And today I'm going to be talking about the Poisson distribution. Please make sure to check all of my notation and language use with your professor because it may vary. We're talking about the Poisson distribution today, and it's not called the Poisson distribution. And so, like with any probability distribution, you'll want to know when to use it. So first of all, this is a discrete probability distribution as opposed to continuous. So you'll want to use it when your outcomes take on non-negative integers as values. So usually something you can count, that's discrete. The other thing is, usually when we use a Poisson distribution, we're recording the number of events that occur in a given time period. So a common example that I see a lot is maybe you're talking about a call center and you want to know how many calls do they get within the hour, or what's the probability that they get X number of calls within the next hour. Something like that. And there's some other assumptions that you need to have to use the Poisson distribution. So independence, and what I mean by that is the number of events that occur within a given time frame is independent from the number of events that occur during a separate time frame. So here you could imagine maybe if they get a lot of calls in the first hour, then that means they're going to get more calls in the second hour. That would violate independence. So we need to have that form of independence to use the Poisson distribution. So this is when you use it, so make sure you have that down. As far as how to use this probability distribution, first of all, it has one parameter, so usually it's lambda, and that is the mean of the distribution. It also turns out to be the variance of the distribution. So one special property of the Poisson distribution is it has the same mean and variance, and that's given by this parameter lambda. So again, like any other discrete probability distribution, we kind of want to have a probability density function, or PDF. And if you'll recall the definition of that, it's the probability that a random variable takes on a specific value. So, for example, capital X is a Poisson random variable. Then the PDF of X is given by this formula. So the probability that that random variable takes on a specific value, little x, is given by lambda to the x. So again, lambda is this parameter here, the mean, times e, which is the mathematical constant e, to the negative lambda, and you divide by x factorial. And that's the probability distribution function. So for example, my previous example was the number of calls within a certain hour. And if you know the average number of calls that the call center gets within 1 hour, then you can plug that in for lambda, and then you can answer the question, what's the probability that they get exactly 2 calls within the next hour? And then you plug in 2 for x. So I'll do an example in a minute. The other thing we usually have for a probability distribution is a cumulative distribution function, or CDF. And there is one for the Poisson distribution, but it's very complicated. It's not really a closed form like this. So we don't work with that. So if you remember, a cumulative distribution function answers a question like, what's the probability that the call center gets 3 or fewer calls? So it's cumulative in the sense that 0, 1, 2, or 3 is included in 3 or fewer. And the cumulative distribution function would tell you that. But with the Poisson distribution, if we're going to answer a question like that, usually we just use the PDF, find the probability of getting 0 calls, find the probability of getting 1 call, etc., all the way up to 3 calls. And then we just add those 4 probabilities. So it's a little tedious, but again, the CDF is not very easy to work with for this distribution. So that pretty much sums up everything you need to know about the Poisson distribution. I went through when you use it and what assumptions are made about it. the mean and variance, which is given by this parameter, and the PDF and the CDF. So now I'll just do one example to show you how to use the PDF. So again, let's say that capital X is a Poisson random variable, and remember we have to specify what lambda is. So we'll say with mean 5. And then you want to ask, let's see, what's the probability of getting 4 calls within the next hour? And so the way you do that is you say the probability that capital X equals 4, and you may need to look back at the PDF for this one. Remember, we take lambda, which is 5, so I'll write it down here. Lambda to the x, so 5 to the 4. Then e to the negative lambda, which gives us e to the minus 5, divided by x factorial. Okay, and so if you plug this expression into your calculator, you should get 0.175. So just to check, first of all, it makes sense that it's between 0 and 1 because it's a probability distribution. If you get anything negative or anything greater than 1, you know something went wrong. And then the number says there is a 17.5% chance that they get exactly 4 calls within the next hour, given that the mean number of calls is 5. So again, because we're using the PDF, it tells us the probability of exactly 4 calls. Sometimes you may be interested in the probability of 4 calls or fewer, or more than 4 calls. Like I said earlier in the video, to do that, it's best to repeatedly use the probability density function, and then add them all together, subtract them from 1 if appropriate. Again, so this is your final answer to the number of, or the probability of 4 calls within the hour. I hope this explains the Poisson distribution and how to use it. If you have any more questions about it, ask your instructor or come into the Economics Tutoring Center.